So, first of all, happy Independence Day to all of you. So, welcome all to this third session for the course Essential Mathematics for Machine Learning. Today, what I have planned to cover is I'll discuss what is Eigen Decomposition, and also I'll talk about singular value and singular value decomposition, how we can find it and its applications. Okay. So, at any point, if you have any kind of doubt, you can unmute yourself or you can type in the chat box, whichever is more comfortable to you. I'll be monitoring both, so you can stop me anytime and ask it. Okay. So today I'll be discussing more of questions that are related to assignment. So yeah, that's what my plan for today is. Okay. So let's talk about first of all what's spectral decomposition or eigen decomposition. Last time or in week 2, we all talked about how can we find eigenvalue or eigenvector of a given matrix. Okay. Okay. So now, let's say if you have some square matrix A, okay, then you can find its eigenvalue and eigenvectors. Okay. So if you can find its eigenvalue and eigenvector, then these matrices have a very nice property, that is, so let's say if you have A and let's say A is a 2 cross 2 matrix with eigenvalues, let's say lambda 1 and lambda 2, okay, and you have corresponding eigenvectors v1 and v2. Okay, now if you write these eigenvectors as a column matrix, so let's say you construct a matrix P, writing v1 as your first column, v2 as your second column, and you construct another matrix B where your diagonal elements are your eigenvalues and rest everything is 0. Okay, then you can write your matrix A in form P multiplied by D into P inverse. Okay, so you can do this thing. Okay, so this is something which is referred to as eigen decomposition or your spectral decomposition. Okay, so if you have let's say a square matrix, and now you can see that I'm calculating inverse of this matrix P. Okay, so if I have now n linearly independent eigenvectors, if your matrix is n cross n, okay, if I have n linearly independent eigenvectors, then I can write A in form P dP inverse. I just told you how can we find this P and okay. Chandrape, you are asking about how to find P inverse. Okay. Okay. So for if you have any general matrix, then whatever you learn till class 12, you can use that some elementary operation or those kind of tricks to find P inverse. But one thing that was mentioned in the lectures in this week, if you have, let's say, symmetric matrix, okay, if you have a symmetric matrix, then to find P inverse, you can just transpose that particular matrix. Okay, so for symmetric matrix, so if you construct a matrix out of its eigenvectors, that particular matrix is orthogonal matrix. Okay, then you can just to find P inverse, you can just do P transpose. Now, for any arbitrary matrix, you need to go through all the steps of finding your inverse that you probably learned in class 11th or 12th. Was I clear? I hope so. Okay. So I just told you how you can find the matrix P. Matrix P is nothing, but you just stack your eigenvectors in form of columns. Okay. And your matrix P is a diagonal matrix with diagonal elements as your eigenvalues. Okay. So one thing that I thought I would just include that was not sort of explicitly mentioned in the lecture. So if for any matrix A, you are able to find such eigen decomposition, let's say for A, you were able to find PDP inverse, then let's say you want to calculate A to the power 5. Okay. Now, let's say if you have a diagonal matrix B0, 0, what is this to the power 5? Okay, so there is a very nice property of diagonal matrix. Let's say if you have a diagonal matrix and you want to raise it to some power, okay, then what you just do is you just so you raise the diagonal elements to the same power. Okay, so your calculation becomes very easy because matrix multiplication is not straightforward, right? So in case you have some diagonal matrix, what you can do is you can just take the diagonal elements to that power. Okay, now if you look at this matrix and if you are able to convert it into the form of eigen decomposition, what you can do is let's say you want to multiply PDP inverse again with PDP inverse, so it is 5 times, so this is PDP inverse, PDP inverse. What eventually you get is so you can see that this P inverse into P would be identity. Again, this P inverse into P would lead to identity. Same over here. Okay, same over here. So what eventually you are left with is, so you will get P d to the power 5 P inverse. Okay, and as I showed you that finding d to the power 5 is very straightforward. So like if in some application you have to find some matrix to some power, high power, let's say P a to the power 1000 or 2000. So you need not explicitly calculate that. You can first transform it to its eigen decomposition and then calculate in this way. Okay. So one thing is this that I wanted to tell you. Yeah. Another thing is if you have a symmetric matrices, as I mentioned some times ago regarding this question that some of you asked. So if you have a symmetric matrix, then the eigen decomposition always exists. Okay, I'll come to the point like for other matrices when the eigen decomposition exists or when it does not exist. But if you have a symmetric matrix, then the eigen decomposition will always exist. Okay, and there is a unique property that this matrix P that you obtain from its eigenvectors is an orthogonal matrix. Okay, so for symmetric matrices, your eigen decomposition, this PDP inverse, reduces to PD P transpose, because for orthogonal matrix, its inverse is nothing but its transpose matrix, right? Okay. Okay. So here we solve. Okay, is so in case of symmetric matrix, if your let's say your A matrix is given to be symmetric matrix, then the P matrix that you will form will be an orthogonal matrix. It's not
Sir,
yes.
excuse me. Sir,
Hmm.
can you please explain how that inverse P inverse become P transpose, sir?
Okay, I'll explain it to you. See, what happens is, so if you, how do we obtain this matrix P? So P matrix is obtained by stacking the eigenvectors of your this orthogonal, sorry, eigenvectors of your matrix A, right? So in case of symmetric matrix, what happens is the eigenvectors that you are getting are orthogonal to each other. Okay. So what is the property of orthogonal vector? So if you, let's say you have two vectors v1 and v2 which are orthogonal to each other. So what you get? You get v1 dot v2 is
Zero.
equal to 0.
Okay, okay, sir.
Okay. So now if
Hmm.
your eigenvectors are orthogonal, so if you just multiply, let's say this is v1, this is v2, okay, and let's say this is v1, this is v2. So when you sort of multiply these two things, this turns out to be something like this v1 dot v1, this is v1 dot v2. So these entries turn out to be 0, sorry 1, and rest of them turn out to be 0. This is how you see this relation.
Okay, 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 sir.
Okay. Okay. So this is a sort of a beautiful property of symmetric matrices. Okay. that we will also see when we talk about singular values, that we will use this property later on. Okay. Okay. So here is a question very much related to one that is given in your assignment. Okay. So I think only the matrix structure is different over there. Everything else is same. Okay. So this spectral decomposition is another name for your eigen decomposition. Okay. So we are given with a matrix and we have been asked to find its eigen decomposition or spectral decomposition. Okay. So what we need to do is we need to do two things. First of all, we need to find its eigenvalue and eigenvector. Okay. Okay. And then we just need to write this in this form. So you can observe over here also that the matrix that is given to us is actually a symmetric matrix. Okay. So we just need to worry about finding P, and then P inverse will automatically be calculated. Okay. By just taking the transpose. Okay. So now I'll sort of solve this complete example so that if somebody had any doubt with eigenvalues, eigenvectors, that would also be clear. So let's say my matrix A is 3, 2, 2, 3. How do we calculate eigenvalues? So eigenvalues are solution for lambda. So we need to solve for lambda over here. So the determinant of A minus lambda I is 0, right? Okay. So if we write this matrix in this form, this is 3 minus lambda. This term is 0, 2, 3 minus lambda. This is 0. So what does this mean? This means 3 minus lambda square minus 4 is 0. So this is lambda square plus 9 minus 6 lambda. It's 0. This is lambda square minus 6 lambda plus 5 is 0. So we can write lambda square minus 5 lambda minus lambda plus 5 is 0. So this would imply lambda minus 5 minus 1, lambda minus 5 is 0. So what are values of lambda that we obtain? In option solved diagonal matrices. Yeah, so I know that I can straight away look at the options, but I just wanted to solve for someone who don't know how to calculate eigenvalues. Okay. So the values of eigenvalues that we get are lambda is equal to 5 and lambda is equal to 1. Okay. So as someone mentioned in the comment, that even if you look at the options, so in every option you have a same thing, that 5 and 1 is already given as a eigenvalue. So you can just observe the option and know the eigenvalues also. Okay. Okay. So now we need to find eigenvectors. Okay. So let's say we are trying to find eigenvector for lambda is equal to 5. Okay. So what is an eigenvector for lambda is equal to 5? It's a vector B satisfying A minus 5i times V is 0. Okay. So what was my A matrix? 3, 2, 2, 3. So what do I obtain? This is 3 minus 5. I get minus 2, 2. Again I get 2 minus 2. This is V1, V2, let's call it. So this is 0, 0. So what does this imply? This implies that my minus 2 V1 plus V2 plus 2 V2 is 0, or V1 is equal to V2. Okay. So a choice for my V can be 1 comma 1. Now because like we just want this matrix that we are forming P to be orthogonal kind of a matrix, so it is like better to normalize this particular vector V. Okay. So if we normalize, what do we obtain? We obtain 1 by root 2 and 1 by root 2. Why did we normalize it? So that we can straight away write that our P inverse is P transpose. So if you look at this thing, so where we had V1 dot V1, so we want this quantity to be 1. Okay. So that's why we normalize this matrix, this vector. Okay, so we obtained our eigenvector for lambda is equal to 5. Okay, same thing we need to do for lambda is equal to 1. Okay, for lambda is equal to 1, so a minus 1 identity times v is 0. So this is 2, 2, 2, 2, v1, v2 is 0. So this implies that 2v1 plus 2v2 is 0, or v1 is equal to minus v2. Okay, so again a choice for v can be 1 comma minus 1, or my v can become minus 1 by, sorry, this is 1 by root 2 and this is minus 1 by v. Okay, right. So now we have obtained our vectors. So now it's time to write the eigen decomposition. So this 3, 2, 2, 3 can be written as, let's see, somebody wants to join. No. Okay. So this can be written as, so let's rewrite the first eigenvector as the first column. So this is 1 by root 2, 1 by root 2, and this one is 1 by root 2. This is minus 1 by root 2. Okay. And what is my diagonal matrix? Diagonal matrix is 5, 0, 0, 1. Okay. And now what I want to do is, I want to write the inverse of this matrix. Okay. As we observed that our A matrix is already a symmetric matrix. So in order to obtain its inverse, we just need to find its transpose. So what is its transpose? This is 1 by root 2, 1 by root 2. This is again 1 by root 2 and minus 1 by root 2. Okay. This is one set of solution. Okay. Another set of solution is, if you would have, see, the condition that we got over here is that v1 is equal to minus of v2. So you could have also obtained minus 1 comma 1 by root 2 and 1 by root 2 over here. So corresponding to this, you could have got another solution. Okay. So let's match if this particular thing that we have obtained matches with any of the option. Okay. So now as you can see, we had this minus 1 by root 2 at the fourth position, but none of the options has this minus sign on the fourth position, right? So the person who has created this question has gone for this option. Okay. So what he chose is, he chose 1 by root 2, 1 by root 2, and minus 1 by root 2 comma 1 by root 2. Okay. This is perfectly fine, right? So what are the options with minus 1 by root 2 at these positions? So this is this particular option, because we don't have a minus here, we just have a minus over here. So this option is the correct answer. Okay. So this is how you can obtain eigen decomposition for the question that is given to you in the assignment also. Okay. Now, till now, any doubt in eigenvalues or eigenvector? How do we find them, or how do we obtain the eigen decomposition of any matrix? I'd be okay to answer them. Okay, then probably I'll move ahead. Okay, so here is one more question, very similar to what the current assignment has. So we are okay. Somebody has some. Yeah, Rohini, you have some doubt.
So, why are you writing this thing?
So isn't
My, in last answer, minus sign is in second column, second row.
see? Okay, so see, whenever you obtain an eigenvector for some matrix, eigenvectors
Hmm.
are generally not unique. Okay,
Oh,
so
yes.
eigenvector is not a vector, but a space, a complete space. So let's say, what is the definition of an eigenvector? So that AB is some lambda times B. Okay.
Yes.
Now let's say you took V as some C times V. Then what is A of CV? This would be C times lambda V, which is lambda CV. So if you have V as an eigenvector for some matrix, then CV is also an eigenvector for the same matrix. So this generally is not a vector, but a space that is formed by eigenvector corresponding to an eigenvalue. Okay. Now, if you look when we solved for the second eigenvector, we got a condition. We never get a unique solution. We generally get a condition on when we try to solve for eigenvectors. So what did we get? We got V1 is equal to minus of V2. Okay. Now there were two possible options. Either we could have chose first position as -1, or we could have chose second position as -1. So when I was solving earlier, I chose second position as -1 and first position as 1. But the option didn't match then. Okay, so they didn't had minus sign in any of the option at fourth position. So I looked for the other possible option. So I took minus at the first position and then obtained the solution. So that option matched. Okay. So am I clear? So both are correct, but because the answer have that option, so I wrote this one also.
Yes, sir.
Okay. Okay. So now let's get to this question. Just have a minute to read this question. So you are given with some matrix. Okay. So you are given that A is some matrix, and you are given that its eigenvalues are 4 and 9. Okay. And you are also given that eigenvectors corresponding to these eigenvalues are these two. Okay. Now they have asked you to find the original matrix. Okay. So this is the question that they have asked. So how do we tackle this?
Sir, we know AB equals to lambda V.
We
So
know AB is equal to lambda V. Okay.
A इक्वल्स टू V इनवर्स लैम्डा V अगर करें तो हमें A की वैल्यू मिल जाएंगी.
But that V over here is a vector. Okay. It's not a square matrix. So we can't find its inverse. Inverse is not possible for this. Think in terms of this Eigen decomposition that I just told you.
Yes.
Okay, so I told you that A can be written as PD P inverse, where P is a matrix consisting of only your eigenvectors. Okay, so you are given with eigenvectors. So we will just write it in this form. This is 1, 2, 2 minus 1. Okay, now what are my eigenvalues? So this first column corresponds to lambda is equal to 4. So I will make this 4, 0, 0, 9. Okay, and now I want to find the inverse of this matrix. Okay. Okay, so one thing that you can see is this is also a sort of orthogonal matrix, but it's like v1 dot v1 is not getting to 1. Okay, so if you look carefully, that if you take 1 to this, let's call this v1, let's call this v2. So v1 dot v2 is 0. So this is 1 times 2 minus 2. Okay, so in order to obtain the inverse, we need not do all those steps or the, okay, so we can play smartly. Okay, so let's say if we multiplied it with its transpose. Okay, so its transpose is this is 1. Actually P inverse is not P transpose over here, because the length of these vectors, this column vectors, is not 1. Okay, so we need something extra over here. So this is 2 minus 1. Okay, so what do we obtain? This is 5. This is 0, 0, 5. Okay, so P transpose is P into P transpose is 5, 5. So what does this mean? That 1 by 5 times of P transpose is identity. So what is P inverse then? P inverse is 1 by 5 times of P transpose. Okay, I was talking about length of vectors. Okay, I'll make this thing more clear. Okay, let's say I'll make this thing clear for you. Okay. Let's say you have a matrix where V1 is your first column. Okay, V2 is your second column. Okay, now you took its transpose. Okay, I'm just trying to show you what happens when you multiply a matrix with its transpose. Okay, so what is the first element that you'll get? Okay, so how do you obtain the first element of this matrix? So you will multiply this thing. Okay, with okay, let me write it other way around. So let's say this is your V1, this is your V2, and this is your V1, this is your V2. Okay, so how do you obtain the first element? So this is V1 multiplied by the first column, first row with the first column. So what do you obtain? You obtain V1 dot V1, right? What is the second thing that you obtain? Second position you will obtain as this particular thing multiplied with the second one. Okay, so this is V1 dot V2. So what I was saying is, if I had length of these row vectors as 1, then I would have obtained 1 over here and 0 over here, because they are orthogonal, right? And again 0 over here and 1 over here. But their length was not 1, their length is 5. Okay, so that's why I had to divide it as 5 to obtain the inverse of this thing. Am I clear? Whoever asked this thing? Ayana,
Sir, please explain again.
can you please repeat?
Please explain again.
Okay, what I was saying is, so if you have a matrix P which is orthogonal, okay, then what happens is, so let's say you have a matrix, this is let's say call this A, and this is A transpose. Okay, if you multiplied these matrix and your rows are orthogonal, let's say, okay, so what will happen is this position will be V2 dot V1. If you look carefully, this thing is clear. How do we obtain till now this multiplication? This is V2 dot V2. Okay,
Yes, sir.
now if my V1 dot V1 was 1, okay, then and this V2 dot V2 was 1, then this A transpose would have been inverse of my A, right? But if you look carefully, my V1 dot V1 is not 1, but it is 5. Again, V2 dot V2 is also 5. Okay, so rather than obtaining P into P transpose as identity, what I obtained was P into P transpose as 5 times identity. That's why my P inverse is not P transpose, but it is 1 by 5 times of P transpose. Am I clear?
Yes, sir.
Okay. Okay. So now what it is, this is 1, 2, 2 minus 1, 4, 0, 0, 9. And now I will write transpose of this matrix. This is 1, 2, 2, 1 multiplied by 1 by 5. Okay. So if you will multiply all these three matrices with a factor 1 by 5, you will obtain your matrix A. Okay. So just to recap, what was my question? My question was, you are given with two eigenvectors and the corresponding eigenvalues. Okay. And you were asked to calculate the matrix A. Okay. So what I did, I wrote these eigenvectors as P, D my diagonal matrix, and then P inverse I calculated. and then multiplied them to obtain A. So you have a similar question in assignment, you can do this question. Okay. 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 So I won't do this matrix multiplication. You can probably do this. Yeah. Okay. So now the next question that comes is, can we always find an eigen decomposition? Okay, because you can see that eigen decomposition is of some use. At least you can find power to some matrix. You can decompose the matrix to store it in a smaller way and those kind of things. But can we always find eigen decomposition? Okay, so answer is no. Like we can't always. Okay, so the next question comes is, when can we find? Okay. So one thing that I already mentioned is for symmetric matrix, you can find always. Okay. And the answer to any arbitrary matrix is, if you have n linearly independent eigenvector, okay, then you can find eigen decomposition. Okay, one answer is that. Yeah, if we look more deeply into it, so let's say if you have all unique eigenvalues, okay, let's say you have unique eigenvalues, then also eigen decomposition is possible. Okay, so this property is sort of called as diagonalizability. So when can you diagonalize a matrix and when you cannot diagonalize a matrix? Okay, so another thing is just a sort of note that let's say you have lambda, that an eigenvalue, let's say lambda I, that is occurring, let's say 3 times. Okay, now if you have 3 linearly independent eigenvectors corresponding to this, then also you can find eigen decomposition. So for every lambda I, this should be true. So let's say if lambda 1 equal to lambda 2 is equal to 4, okay, then you should have 2 eigenvectors corresponding to this linearly independent ones. Okay. Another thing is, let's say this lambda 3 is equal to lambda 4 is equal to lambda 5, let's say 5, then you should have 3 linearly independent eigenvectors corresponding to this. So whatever is the number of times a particular eigenvalue is repeating, you need that many linearly independent eigenvectors corresponding to that eigenvalue, then you can diagonalize this thing. Okay. So let's look at an example where you cannot diagonalize this. Okay. So this is your matrix. T is equal to 0, 1, 0, 0, 0, 2, 0, 0, 0. What are its eigenvalues? Can someone quickly say what are its eigenvalues?
0, 0, 0.
So one thing that you should remember, if you have a strictly lower triangular matrix or a lower triangular matrix or a upper triangular matrix, then what are your eigenvalues? Eigenvalues are always the diagonal elements. So these are your eigenvalues. So if you had a matrix like, let's say 1, 2, 3, 4, 5 and 0 everywhere, yeah, I think I drew it correct. So then also your eigen values would have been this 1, 2 and 3. Okay. So my eigenvalues are lambda is equal to 0, 0, 0. Okay. Now I need to find the eigenvectors. So what is the multiplicity of my eigenvalue? This is 3. Okay. Now what should my eigenvector satisfy? Eigenvector should satisfy A minus 0 times identity into V is 0. Okay. So what does this imply? A minus 0 identity is just A, right? So this is 0, 1, 0, 0, 0, 2, 0, 0, 0 times of V1, V2, V3 is 0. What does first row imply? First row imply that my V2 is 0. Okay. What does my second row imply? Second row implies that my V3 is 0. Now, how many independent choices I have? I have only one choice left. That is, I can choose any arbitrary V1. So how many independent eigenvectors I can get? I can get only one independent eigenvector because I have only one arbitrary choice to make. Okay, so now you can see that my this number of times my eigenvalue was repeating was 3, but I only got one corresponding linearly independent eigenvector. So for this matrix, we can't find an eigen decomposition. Okay. If I would have obtained 3 linearly independent eigenvectors corresponding to this, then I could have. Okay. So one thing that I don't think would be covered in this course, but just out of curiosity, I can tell you. So for these kind of cases, when you don't have sufficient number of, let's say, eigenvectors, people go for something that is called as generalized eigenvector. Okay. So then they don't obtain an eigen decomposition or diagonalized form. There's something obtained that is known as Jordan canonical form. I think that would be covered in later lectures. Yeah, I think that would be covered. Okay. 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 So any doubt in eigen decomposition and these things, then I'll move to symmetric matrices. I'll wait for 2 minutes, and if you have any doubt, you can ask. Then I'll move to singular values and those kind of things. Or maybe there is a, yeah. Yes, there are sort of different names. So Jordan canonical form and Jordan normal form. Yeah. So uh, when I studied it, I studied as a name. So the name that I studied was Jordan canonical form. So I think that is there in later lectures. I remember it. Okay, maybe we can continue. So, okay, so till now, whatever we did, this eigen decomposition, that was possible only for symmetric matrices. Okay, so we can't even think of finding eigenvalues and eigenvectors for a non-symmetric matrices. Okay, but if you look at the real world data, then what form data exists in? So this is course on essential mathematics for machine learning. So you have some features, right? So let's say you have some house property, housing data, where you have something like number of bedrooms. Okay, you have area, maybe locality. Okay, you have some 5, 6 features, and you have data for, let's say, 1,000 properties. Okay, so in practice, the kind of matrices that you get are never sort of symmetric, right? They are always rectangular in shape. Okay, so we come up with a decomposition called singular value decomposition that is very useful for at least for low rank approximation of these kind of data matrices that we get. Okay, so before diving into this singular value decomposition, let's try to understand what is a singular value. Okay, so now let's say you have a matrix A. Okay, A is some, let's say, m cross n matrix. Okay, now you can't do much with a rectangular matrix, but what you can do is, let's say you found out A transpose A or A transpose. Okay, now if your A was, let's say, m cross n, so what is this A transpose A? This is n cross n, or this is m cross n. Now this thing actually is a square matrix. Okay, And also, one step ahead of square matrix, this matrix is indeed a symmetric matrix. Okay, so now for symmetric matrix, we know all nice kind properties that they have eigen decomposition, their inverse is just their transpose and those kind of things. Okay, so let's define singular values first before getting any further. So let's say you obtain the matrix A transpose A, okay, and your lambda 1, lambda 2, lambda n are eigenvalues for A transpose A, okay. Then square root of these eigenvalues are called as singular values of your matrix A. This is a very simple definition, okay. So if you have, let's say, lambda 1, lambda 2, lambda n as eigenvalues of A transpose A, then your square root of these represented by these sigma i's are your singular values for matrix A. Okay, so here is an example that we are going to do. So I think there is a very similar question again in your assignment. That's why I picked up this question. So let's say you have matrix A, then what you can do is you can just look at A transpose A. Okay, so what is this A transpose? This is -4, -7. This thing is 1, 4 times 4 minus 7, 1, 4. Sorry, this is minus. Okay, so what is this matrix that I obtained? This is 16 plus 1, 17. Okay, this is 28 plus 4, 32. This is -7 again, minus 28 plus 4, 32. This is 49 plus 16, 65. Okay, I hope I'm doing right calculation. If I do some wrong calculation, please let me know. Okay, so this is, yeah. So now what we need to do is we need to find eigenvalues for this. So this have some calculation, so why don't you try first and then I'll try to solve this. So I can give you 2 to 3 minutes and you can let me know what eigenvalues do you obtain for this. Okay. You can just do this A minus lambda I determinant is 0. Calculation would be a bit involved, but you can try. I'll probably use some Python or MATLAB to solve. For the eigenvalues, you can do by hand. So the matrix given to me is -4, -7. Yeah, somebody says 181. Can others try? I think that's correct, but can someone else verify? It's just solving a quadratic equation that you have been doing since class 6 or 7. Okay. So yes, 81 and 1 is correct, but I'll just do some steps over here. 32, 32, 65 minus lambda is equal to 0. Right? What does this imply? This is 17 minus lambda, 65 minus lambda, minus 32 square is 0. So this would imply lambda square. I think it's minus. So this is 17 plus 65. This would be 82 lambda. Okay, I think for you can just recheck your calculation.
Eight.
Okay, I don't think you will get 41. Okay, so
81 plus.
yeah, this is 81 and 1, right? So what is 17 times 65? So I'll use a calculator because I'm sort of lazy.
1105.
Yeah, minus 32 square. So this is 1024, right? So you get, so this is nothing but lambda square minus 82 lambda plus 81 is equal to 0. Now it's quite easy to split, right? So this would imply lambda square minus 81 lambda minus lambda plus 81 is 0. And this is straightforward, right? Now you get lambda is equal to 81 and 1. So when you got your lambdas to be 81 and 1, what are its singular values? Singular values are square root of these lambdas. So what is square root of 81? This is 9, and square root of 1 is 1. So this option is the correct option. So this is how you calculate a singular value. Okay. Any doubt in this? Whoever was getting 41, were you able to get 81? Actually, when you look at these angular values, you will always get positive values only. Okay, so you will never get negative values. That's why you are able to find its square root. Okay. Okay. Okay, I'll move ahead. So now we know what is a singular value. Okay. Now what we want to do is something called as singular value decomposition. Okay. So I'll just write what a singular value decomposition is, then I'll let you think why do we reach this kind of formulation. Let's say I have a matrix A. This can be any matrix. This can be a rectangular matrix too. Okay. So this is factored as U times some sigma V transpose. Okay. And this is how it is factored. Okay. Now, just look at this formula, right? Now, if you do A into A transpose, okay. So what is A into A transpose? This is U sigma V transpose times, now this is A transpose, right? This thing will go this side, so this would be V sigma U transpose. These combined produce, okay. So one property that I wanted to mention over here is, so this U and V are orthogonal matrix again. Okay. So we try to split A such that U and V are orthogonal matrix and your sigma is a diagonal matrix. Okay. This is what we want. Okay. Now, because U and V are your orthogonal matrix, V transpose V would be an identity matrix. Okay. Okay. So factorization of a matrix means you want to write a matrix as product of some other matrices. Okay. This is what a factorization means. So we have, so we tried to write A as product of three matrices over here. That's why we called it as factorization of this matrix. Okay. So yeah, now this thing turns out to be identity. So this is U sigma square U transpose. can you relate this to something like P D P transpose? Now remember this A transpose is a symmetric matrix, right? So can you now tell me what my U should be, what my sigma square should be, and what my U transpose should be? So what is my sigma square? Sigma square is nothing but eigenvalues of A transpose written in form of a diagonal matrix, right? Now what is my P? P would have been eigenvectors of A transpose. So what is my U? U is eigenvectors of my A transpose written in form of columns, right? So now my sigma square was eigenvalues of A transpose. So what is my sigma? Sigma is singular values of A. So what was actually this sigma thing? Sigma was square root of these eigenvalues, right? So now my sigma becomes singular values of A because sigma square is eigenvalues of A transpose. Okay. Now similarly, if you look at A transpose, let me use some other color. Let me use A transpose A. What is it? So this would be, now my A is U sigma V transpose. What is A transpose? This is V sigma U transpose times U sigma V transpose. This turns out to be identity. What are we left with? V sigma square V transpose. Okay. Now again we can infer the same thing. My sigma is singular values and my matrix V is nothing but eigenvectors of my matrix A transpose A. Okay. So if somebody asks you to, okay, so Pradeep, this sigma matrix is a diagonal matrix. Okay, this is of form this. So this is sigma 1 0 0 0 0 sigma 2. So actually this is not a like symmetric matrix, but because the size of this sigma matrix is not always something of form n cross n, but yeah, because this is a diagonal matrix, you can just look it in a way that even if this is not like sigma transpose is not equal to sigma, right? Even if sigma transpose is not equal to sigma, but because this is a diagonal matrix, it's the singular values sort of squares. Okay, this is what is happening over here. So they don't have same size. I'll just take a small example to show you. Okay, so why I wrote that thing as sigma square? Yeah, you are right. It's not a sort of very symmetric matrix. Let's say this is 1 0 0 2 0 0. Okay, now if I multiply it with its transpose, okay, so this is 1 0 1 0 0. This is 0 2 0. So if you look carefully, what you would obtain is this is 1 square, right? And then again this would be 0, this would be 0, and this would be 0, 2 square 0, 0 0 0, right? So yeah, sigma square is a diagonal matrix, but this is I should have written it yeah, I should write it as sigma transpose. I sort of symbolically wrote that because I wanted to show you that, yeah, but I shouldn't have. Yeah, that what you will obtain is that you will obtain a diagonal matrix having all the diagonal entries as sigma square. Okay. I hope, Pradeep, now it's clear. Okay. Okay.
Yeah,
So,
yes, sir. It's clear. Thanks.
okay. So now just a sort of recap for this single value decomposition. So if you have some matrix A, what you try to do is, this is let's say some n cross n. What you try to do is you try to break it as U, sigma, and V transpose. Okay. So now what should be the size of U, sigma, and V transpose? So as you can see, what I said is that your U is eigenvectors for AA transpose. Okay, what is now size of AA transpose? If A is m cross n, then AA transpose is m cross m. Then what is size of this eigenvectors matrix? This should be also m cross n, right? So your m is m cross U is m cross m. So this sigma becomes m cross n, and this V transpose is again n cross n. Okay. So this is something about the size of these matrices. Okay. So if somebody asks you to find out this singular value decomposition of a matrix, then what you will do is, first step would be to find a transpose. Okay. And then find eigenvectors for eigenvalues for this. Okay. How is sigma into sigma is equal to sigma to the power 6. Okay.
So sorry, it is sigma square. You wrote above, no? Sigma into
So
sigma
I
transpose.
modified
In
it. Okay.
case
So sigma into sigma transpose is not sigma square, but I symbolically wrote to represent that whatever matrix that I would be getting, that would be the square of these terms. This is what I meant over here. Am I clear?
oh, okay, sir. Yes.
Okay. Yeah. Okay. So what you will do is, first of all, you will take AA transpose. You will calculate its eigenvalues. Okay. And then the corresponding eigenvectors. Okay. So for sigma, what you will do is, to construct sigma, you will just take a square root of the eigenvalues that you have obtained and write it on the diagonal elements and fill rest of the entries with 0. Okay. And for your u, you will write eigenvectors as columns. Okay. Now again, to obtain a v, you will take A transpose A. Your eigenvalues will again be same. You need not calculate it again. Okay. Then you need to find the eigenvectors and obtain your v. Okay. So I will do some questions related to this. Okay.
Sir, can you just scroll above? I need to see something.
Yeah, sure. Further up.
Yes, sir, it's fine. Now you can go back.
Okay. Okay. This picture that I have included here is directly from the lecture. Okay. Because there were quite a few questions based on these 4 properties, so I've included it. Okay. So now, okay, first of all, I'll sort of just give you motivation why this singular value decomposition is important. Then we'll come back to the properties. Okay. See, many a times when you're doing machine learning or these kind of things, okay, so there will be 2 situations. First is that you have data very big to process. Okay, these are 2 extreme situations that can happen. And another thing is that that you want to find some kind of similarity matrix between some data points. Okay, or you want some representation between these data points which is of some high dimension. Okay, but because of you don't have enough let's say data points or enough clean data points or pure data points, you can't reach to this matrix. Okay, so what you want to do is you want to approximate this matrix. Okay, approximate this matrix with some lower rank matrix. Okay. So in previous lectures also have talked about methods like word to vec or node to vec. So let's say you have a word to vec where you know that if you represent every word as a vector in dimension of 1 lakh, you might achieve very good results. Okay, but representing everything in 1 lakh might not be very feasible to you, right? So what you want to do is you want to represent every vector in, let's say, of dimension 10. Okay, so what is the best low rank approximation or the best low rank representation that you can have? There your SVD helps a lot. How does it help? I'll come to that. Somebody wants to join. Okay. So another thing that I mentioned here was, let's say you have a very big data set and you want a smaller matrix representation for your data set. Okay. Then also what you can do is you can do a low rank approximation. Okay. Can you please mute? Yeah, thanks. You can do a low rank approximation for your the large data set that you have. Okay. For example, if you look at the last lecture on Python implementation, so sir had a image which had, I think, 750 distinct singular values. Okay, so that was a sort of rank 750 image. Okay, so every column that he had was sort of unique, right? So they were not linearly dependent, but 750 linearly independent columns that he had. But if you want to store those many columns, it is very like sort of it would take a lot of space on your disk, right? So what he did was he just took a 50 rank approximation and he was good to go with it. Okay. So in these kind of application, your singular value decomposition helps a lot. Okay. So we will look at what do we mean by K rank approximation. Okay. Then we'll get back to those properties that we are talking about. Okay. Okay. So now let's say I have a matrix, let's say identity matrix, and somebody says me make a 1 rank approximation to this matrix. Okay, so if I write, let's say 2000 or I write 3000, this is some approximation to this matrix. But we need to analyze how good an approximation it is and how bad an approximation it is, right? So any approximation is so if you write any arbitrary matrix, that would be an approximation to some other matrix. But we need to find the quality, how good approximation it is or how bad approximation it is. So how do we do that thing is, let's say you have some matrix A, okay, and this is A approximation. Then you can find a norm of this difference, and that can be used to quantify how good or bad an approximation is. Okay. Okay. So now one of the norm, yeah, that's what I'm saying. Approximation of a matrix is we want another matrix A which sort of preserves the structure of the original matrix, but is of some lower rank than this matrix A. Okay, so by that I mean that it is close to this matrix in terms of some norm over here. Okay, so you can choose your norm on your own, but let's say if I choose Frobenius norm, so Frobenius norm is defined as, so if you have a matrix, this is square root of sum over ij, aij square. So you take sum of all these elements and you just take their square root. Okay. So this is one approximation. Okay. So to answer your question, I'll give you an example. Okay. Let's say you have a matrix 1 0 0 1. Okay. And I have this is my A. Okay. So I have two approximations to it. Let's say this is 2002. Another approximation is 3003. Okay. Right now I'm looking at same rank approximation, but I'm just giving an example. Let's call it B and this is, let's call this C. Which one do you think is more closer to A? So just using the logic or the common sense, which one do you think is more closer to it? B, right? So yeah, so that's what we want to capture mathematically over here. Okay, so that's what we want to do is we want matrix that is close enough to A. And how do we define that closeness? That is through matrix norms. So sir has talked about I think 3-4 norms in the lectures, that is one norm, infinity norm, Frobenius norm, spectral norm. Okay, you can go through them, right? So I'll be just talking about Frobenius norm, okay, because that is important from SVD perspective. So Frobenius norm is nothing but you take square of all the elements, okay, and then you just sum them up and then take their square root. This is very similar to your Euclidean norm that you do in Rn spaces or those kind of spaces. So let's say if you want to take look at this approximation, so this would be Frobenius norm of A minus B, right? So A minus B is nothing but minus 1, 0, 0, 1. So this would be square root of 2. Okay, so and A minus C would be something like square root of 8, right? So yeah, this is how you can look at the approximation. Okay, now getting back to the story. Okay, so I defined Frobenius norm. Now I'll talk about SVD. How is SVD useful in approximation of matrix? Okay, let's say you have a matrix A, which is U sigma B transpose. Okay, now for the time being, let us assume that this is very nice. Okay, let's take this as M cross N. So this would be M cross M. This would be M cross N. This would be, sorry. Okay, this would be N cross N, or yeah, sorry, I'm making a mistake here. This would be M cross M. This would be M cross N, and the last one would be N cross N. Okay, let's say I want to make a dimension, a rank D approximation. So this is a rank D approximation to my matrix A. Okay, what I need to do is, so let's say you have M singular values over here. Okay, so you have some, let's say U1, U2, okay, U3, and so on, right? And you have some, let's say sigma 1, sigma 2, and so on. And here also you have V1, V2. Okay. Now, what I do is I just pick the first D singular values in order of their value. So if my sigma 1 is greater than sigma 2 and sigma 3 and so on. So I just pick them in that order, that I pick the first D ones, okay, and put rest of them to be 0. Okay, or I just ignore those sort of columns. So what is the size of matrix that I would so yeah, so this, what I do is I truncate my sigma matrix just to my first D singular values. Okay, so there are yeah, so then this would be D cross N, right? You will have only D rows over here. I have truncated my matrix at D singular values. Okay, so just to make this thing also multiple, so that I can multiply this, I will also convert it to be M cross D. So what would it be? So this would be just
Sir, can you please explain that one more time, sir?
I'll just finish and then I'll explain it again. Okay.
Okay.
Okay. Okay. So yeah. So I'll just take the first D columns again, and similarly over here I can adjust. Then the product that I get, okay, that would be an D rank approximation to my matrix A. Okay. Okay. As somebody said, I'll just explain it again. So that D depends on your choice. Okay, so that's up to you what rank approximation you want to find based on your application. Okay, I'll just explain it again. This should be. Okay, so I'll explain. Okay, so let's say you have a matrix A, which you have written as singular value decomposition in this form. Okay, so now I'll just split it up. So this is U1. My A is M cross N. So you will get M eigenvectors corresponding over here to make U. So this would be UM. Okay, you will get some sigma 1, 0, 0, sigma 2, and so on till some sigma R, 0, and rest everything to be 0. Okay, and you will get one more, which is your, now because this is V transpose, so you will get these vectors in row form. Okay.
Sir, why are we not getting sigma?
Why are we
That
not
full value, sir?
Okay, so that would depend on the rank of this matrix A. Okay, so whatever is the rank of your matrix A, those many sigmas you will get. Okay, so because this is any arbitrary matrix A, so I have also included some 0 rows over here. Okay, so you will get similarly till some Vn rows, right? Now this is a rank, so the rank of A is R over here. Okay, so in some applications, you might be asked to approximate this matrix A with some other matrix of rank D. Okay, size would be M cross N. Okay, but the rank of the matrix that you would get would be D. Rank as in you studied in first week or second week, that is your number of independent rows or columns. Okay, so how do we obtain rank D? We just truncate our SVD. Okay, so what we will do is, let's say this is my sigma D. I'll truncate to this point. Okay, I'll make a some sigma D, which is a truncated sigma. Okay, let's say this is my D cross D.
Sir, we will put all other values of sigma as 0, sir.
So no, we will modify the size of this U and V also accordingly. Okay, so if we make, just pick the D cross D elements from the top left, right? Okay, so what will be left with over here is, so we would be left with something of M cross D. So what would that mean is that we will just pick the first D columns of U. Okay, and similarly over here we would be left with V cross N, which is the first D vectors of V, rows of V. Okay, now if you would multiply, let's say this is U hat, this is some sigma hat, this is some V hat. If we multiply these things, U hat, sigma hat, and V hat, we will get some A hat, which is again of size M cross N. M cross N. Okay. Now, even though the size remained same, whatever this A hat we obtain is of rank D. Now, there is a very celebrated theorem which says that if you like obtain an approximation via this method, this is the best approximation that you can get. So there is no other matrix of rank D which is closer to your matrix A in terms of Frobenius norm. Okay, so what I mean is, so let's say you want to minimize over all A belonging to R M cross N. Let's call it B. Okay, so this is such that your A minus B Frobenius norm, you want to minimize this quantity, right? So the value of B that you would obtain is your A hat that you obtained via this method. Was I clear?
Okay, sir.
Okay. So
Sir,
B
explain
would be D
again.
cross N. B will be D cross N. Yeah, somebody was saying something.
Sir, please explain again.
Which part do you want me to explain?
Sir, truncate matrix, I understand. After that,
Okay, so what I meant is, so you got an approximation for A, right? So you got A tilde, which is an approximation to A. So why only you want this approximation via SVD thing? You want that because there is a theorem, okay, very famous theorem, which says that if you find A tilde via the method that I mentioned via this approximation, that is the best approximation. Okay. So what I mean by best approximation is, if you take the A minus A tilde norm, okay, in terms of Frobenius norm, this is always less than equal to norm for any B matrix which is of rank D. Okay, so if you look at all possible matrices of rank B, rank D of size M cross N, A tilde is closest to A. Am I clear? Whoever was speaking, am I clear? And Prathamesh, am I clear?
yes, sir.
Okay. So this is sort of closest that you can get to A. Okay. 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 Now there is one topic that I'll cover before going back to where we were. Okay. So this is called quality of approximation. Okay. So this is a quantity. So let's say for a matrix A, you obtained sigma 1, sigma 2, and sigma n as your singular values. Okay. Now, if you obtain an M rank approximation, then you will truncate till sigma m, right? Beginning from sigma 1, you will truncate till sigma m. So, how good this approximation is, that quality of approximation is given by sigma 1 square plus sigma 2 square till sigma m square divided by sigma 1 square till sigma n square. Okay, this is the quantity. So there is a question in your assignment where you are given with five, I think, singular values, which are, I think, 1, 2, something, 3, and x comma y. Okay, and you are again given with the value of your quality of approximation. Okay, and you are also given with what is value of x plus y, and you need to find x and y. Okay, so I'll do a similar question but at a much smaller scale. Okay, so let's say you have only two singular values. Okay, one is 4, another one is x. Okay, now what is given is that the quality of approximation is 0.8, and we have been asked to find what is the other singular value. Okay, so let's say what we know is that let's say we did a one rank approximation. So what is the quality of my approximation? This would be 4 square. So sorry, so this is square root of 4. This lambda is 4. Okay, not the singular value, but lambda is 4. So what is my singular value? Sigma I would be 2. Okay, lambda is 4. So my sigma I would be square root of 4, which is 2. So what is my quality of approximation? This is 4 divided by 4 plus x square. What it is? The value that I'm given is 0.8. Okay. So we can just take that side and I will obtain, so this will be 3.2 plus 0.8 x square. So I can just multiply it by probably 10. So this would give me 32 plus 8x square. I think I can divide it also by that. So x square would be 1 and x would be 1. Because my singular values are always positive, so x would be 1. Okay. So you have a singular question, there you have two variables. So you will need to, so there is one more equation, extra equation given. So you will have to solve for both x and y over there.
Now, what is mean by rank 1 approximation or rank 2 approximation?
So as we were doing here, so how many top singular values you are choosing? So this was a D rank approximation. So I was taking the top D singular values. So if I took only first singular value, that would be rank 1 approximation. If I took two singular values, that would be rank 2 approximation. Okay. And when we come to this formula, rank 1 approximation would mean sigma 1 square divided by everything down here. And rank 2 approximation would mean sigma 1 square plus sigma 2 square divided by everything down here. Okay.
Okay, sir. Okay.
Okay. Okay, so now getting back to these properties that are related to my singular value decomposition. Okay. So let's say if you have again, if you have a matrix A, okay, which is given by let's say U sigma P transpose. Okay. So now what the first point says is that the range of your A. So A is also a linear transformation. You know that, right? So every matrix corresponds to a linear transformation and every linear transform corresponds to a matrix. Okay. So the range of A is given by the first R columns of your matrix U. Okay. So you obtain your matrix U. If you just look at the first R column, that forms a basis for range space of A. Okay. Okay. Now, so yeah, again, one thing is that the rank of this matrix is R over here. That's why we are looking at first R columns. Okay. The second thing is the null space of A is given by the n minus R columns of B or the n minus R rows of B transpose, or whichever way you want to say. Okay. So if you have A, it is mapped to two things. So let's say there are two divisions. So this is first R columns, this is U, and this is, wait, I'll draw a better figure. Okay, so you have a matrix A. Any matrix A have two components, right? If you look at rank nullity theorem or those kind of things, it has two components. One is its rank, another is its nullity. Okay, so the range space or the rank part of it is given by the first R column of U. Okay, so this, let's take this thing this way. Okay, and so the next part is given by, so this is rank, and this nullity is given by the n minus R columns of V matrix. Okay, now if A is a linear transformation, so is A transpose. Okay, now the range space of A transpose, this is range, okay, is the first R columns of B. Whatever is left is the range of A, and whatever goes here is your null space of A transpose. This is M minus R column. Okay, so yeah, this is something that you can look at. So there is a question based on this. We will try to like break down every option that is given over here. Even if some option is not correct, what would have been the correct option in that case? Okay, so that you understand this thing better. Okay. So yeah, so what you are given is you are given a matrix A and its singular value decomposition is given to you. Okay, so the first option says that the null space of A transpose is 0, 0. Okay, then you have to find what is the range space of A transpose. Okay, now if you look at this thing carefully, what is the null space of A transpose? The null space of A transpose is the last M minus R column of U. Okay, so now the null space is 0, 0. That means there is no element in null. That is the dimension of null space is 0. Okay, right. So now if you look at your A matrix is 2 cross 3. Okay. A transpose is 3 cross 2, right? So A transpose is a map from R2 to R3. So you will multiply it with a matrix of size 2 cross 1 to obtain a matrix of size 3 cross 1, right? So this is a map from R2 to R3. Okay. Now first thing that you should look at is that your null space is of dimension 0. So what is the
Sir,
dimension?
can you please explain R2 to R3, sir?
Okay. So let's say let's say you have a matrix A which is of size m cross n. Okay, so how do you obtain T of x? You obtain T of x by multiplying A with that vector x. Okay, so what is meant by let's say this is some r to the power something to r to the power something. Okay, now if let's say this A is m cross n, in order to multiplication to hold, what should be the size of x? It should be n cross 1. Is this clear that it should be n cross 1 so that these two things become compatible? This much is clear, right? Whoever asks that why this should be n cross
That's
1.
me, sir. It's not clear, sir.
This is not clear why this should be n cross 1. Okay. So if you have two matrices A and B, let's say this is of size m cross n and this is of size p cross q, you can only multiply A and B if your n is equal to p. Okay.
Okay, sir.
So,
Yeah,
okay. How do you multiply two matrices? Let's say this is 1, 2, 3, 4, 5, 6. Okay. And this is 1, 2, 1, 1, 0, 0. Let's say. Okay. And 2, 3. So you multiply this first element with the first element plus second element with the second element plus third element with the third element. Okay. That's why what we want is that the number of columns here should be equal to the number of rows. That's why we want n is equal to p. Okay. Now using the same point over here, that my x should be n cross 1. Okay, so x is an element of your domain set, right? So this should be r to the power n. Okay, now if your m cross n, if you are multiplying an m cross n with n cross 1, the size that you obtain is, you just forget about the middle things. That is what is left with you. Okay, so this is n cross 1. That's why it is Rm. So this is a map from Rn to Rm. The same thing over here also. So this was in 3 cross 2 matrix. That's why it is R2 to R3. Okay. Okay. Now, because my null space is a sort of just 0 element, its dimension is 0. So now by rank nullity theorem, what should be my dimension of range space? It should be 2. So first thing is that you should look for 2 elements in the range space. Okay. Now, if you look at range space of AT, it is given by the first R column of P. So we will look at first 2 columns of V. Okay. Now this is V transpose. So we are looking at first 2 rows of V transpose. Looking at first 2 columns of V is similar to looking at first 2 rows of V transpose. Okay. So what should we have obtained? This is 1 by root 2, 1 by root 2 and 0. Another is 1 by root 18, whatever it is. These 2 rows we should have obtained. Okay. Now, because we are just looking at the representation of this particular space that would have been spanned by this and the representation of this, even some scalar multiplication of it would help. So what they have done is they have just ignored the denominator part, because that is just the scalar multiplication of this. Okay, so they have written 1 1 0 and 1 minus 1 4. So this option is correct, right? So this option that we have is an correct option. Okay, similarly we will break the other parts also. Okay, so the second part is also same. Second part says that the null space is again the same. So by our whatever properties are mentioned over here, what we should have obtained is, we should have obtained first two rows of V transpose. But if you look over here, what they have written is the third row of this particular thing. Okay, that too with some sign differences. So the second option is not correct. Okay, we will look at every example because there are, I think, 2-3 questions related to this in this year's assignment. So yeah, let's look at the third one. Okay.
Sir, 1 minute, sir. How are we
Yes.
getting that R there, sir?
How are we getting? Okay, so that's a sort of symbolic. You could have got any other space also. I'm just
No, it's not that, sir. Smaller M minus R, no, sir. Rank.
okay, this rank R.
Yeah.
Okay, so you know something called rank nullity theorem. Okay, I'll tell you what it is. Okay, so let's say you have a map from a space B to some W. Okay, so first of all, tell me, do you know what rank is and what nullity is?
Sir, rank means independent vectors, no, sir?
Right. So if you convert this T into some matrix, then it would mean the number of independent columns or rows that this thing has.
Yeah.
Right.
Sir.
Okay. So yeah. So what rank nullity theorem means is rank of B is equal to this is rank of T plus nullity of T. Or I would write dimension of V over here. Okay. This is a very famous theorem. Any linear algebra book would have this. Okay. So here I use the same thing. So this R over here is the rank of A. Okay. Rank of A transpose, right?
Okay,
So
sir.
what I did is my nullity was 0. Okay. So now I was looking for rank. Rank is the number of linearly independent element in range space of A transpose or A. So if you are looking at rank of T, that would mean as the number of independent element, okay, in range space of T. Okay.
Okay,
Now, we are given that the range of this A transpose is given by R column, that would implicitly mean that this A transpose is rank R matrix. Okay. So because this
Okay,
map was from R2 to R3, right? So this dimension of V, this is a V to W, so dimension of V was 2. That would mean that the rank of T or the range space of T has 2 elements. That's why I picked first 2 elements from here. Now is it clear?
Okay, sir.
Okay. So yeah,
Okay,
so
sir.
if we look at now a third example that says that my null space has 1 element. Okay. Now if you look at this, null space of A transpose is given by last M minus R column. Okay. So now you see that this U has 2 columns. So M is 2, right? Now if you look carefully, this is 1 minus 1. So this is the last column of U. Sorry, this is the column. Sorry. This is 1 minus 1. Okay. So what is value of R? R is 1 because M minus R is 1. So because we have one element over here and it is saying that the null space should have M minus R elements. So my M minus R is 1 and M is 2, that would mean R is 1. Right. So what is the value that we should have in range space? Range space should have R columns of V, okay, or the R rows of V transpose, okay. So what should have been my range space of A transpose in third case? That should have been just the first row of V transpose, which is equal to 1, 1, 0. So this option is incorrect, but if somebody would have replaced this with 1, 1, 0, then this option would have been correct. Okay. Now let's look at the last one also. This is quite straightforward. So it says that the null space of A transpose has two elements. One is 1, 1 and another is 1, -1. So null space can have m minus r columns, right? So this is 1, 1. So it has 1, -1 and again 1, 1, right? So it has already two elements. So what is the value of r? Now m minus, so this 2 minus r is 2. So what is value of r? R is 0. So my range space should have 0 element. It should have no elements. Okay, so this option is also incorrect. Okay, any doubt in this? I would be happy to answer. Okay. So for today, I had only this much planned. I'm sort of stopping 15 minutes early today. So if anybody has any doubt, I would be happy to clear. Okay, so this SPD thing is sort of calculation heavy. That's why this kind of don't get to us in the first go, as per my experience or when I also studied. So you are doing this course, that's more than good, but